Okay, I want to hit some popular pitfalls on this worksheet. Number 2, I suspect that many of you got to this point and had a negative 176. And you're like, I can take the square root, but I can't take the square root of a negative. So I'm just going to go, there. All better. Know that I will hunt you down and light you up if you just start throwing in and taking out negatives just haphazardly because they're convenient. Okay? There's a reason, like, you're right, you can't take the square root of a negative. Okay? So you messed up somewhere. I suspect that you failed to incorporate the negative 60 for the displacement. Okay? Big picture statement right here. If I give you a value for a vector, so something that has magnitude and direction, and I give you the number, I give you the magnitude, you must assign a positive or negative value to that, or positive or negative sign to that. Positive, I haven't really, I mean, it's positive. I didn't really like harp on that. But if negative, you don't include the negative, you're toast. Like, that's the thing. Okay? So displacement, velocity, acceleration, there's more to come, but those are your 3 vectors right now. If I give you a value, give you a number, there needs to be a direction associated with that. Okay? I gave you 60 meters. Your delta x is a negative 60 because you started up here, final minus initial. Good with that? Okay, that was a similar thing to a skydiver problem. Okay? And then when you take the square root, it's plus or minus, and you pick negative because it's moving downward. Okay? Number 3, the whole point of that question was to employ one of your fun facts of free fall. Part A, there's actually 3 different correct ways to solve for that, all of which required a fun fact of free fall. Okay. One way would be to recognize that it starts on the ground, ends at the ground, so your displacement is 0, and it took 8 seconds to do that. Okay. My guess is many of you didn't do that. Many of you said, well, I know that at the highest point I know something about the highest point, fun fact, free fall, velocity is 0, but did it take 8 seconds to get to the top? It took 8 seconds to come back down. So how long does it take to get up to the top? Half that time. Okay. So 4 seconds. Okay. Ready for this? This is a very popular error that will haunt you in this chapter and next if you don't get this. If you say velocity is equal to 0, that never happens down there. That's not in free fall. You're on the ground. There's other forces besides gravity acting on you. Okay? The only time 0 meters a second happens in free fall is at the very highest point. Always. Okay? Do not put 0 on the ground for velocity. Please. It is moving. Drop a bowling ball on your foot, it hurts. Why? It's moving when it hits your foot. Okay? Everybody, like, it'll be a popular error. Don't be that person. Okay? Good with that? Number 4, conceptually, how fast is it going right here? If I throw it up at 15 meters a second, how fast is it going right there? If I throw it up at 15 meters a second, how fast is it going right here? 15 meters a second downward. Just as if I took the ball and I threw it downward at 15 meters a second. Okay. Do they hit at the same time? No, that is not what I'm saying. But when they do hit, their speed will be identical. Good with that? Okay. Last one, number 5. I find it interesting that more and more students get this right as the day goes on. First hour, I think I had one kid get it right. Like, I wonder what things you're referencing. Okay, this is a hard problem. Most of you got to here. Or a lot of you got to there. Okay, that's half of it. Okay, let's pretend that your gas light is on, you're like close to empty, you're trying to make it to a gas station, you see there's a gas station in the distance, but you're at a red light. You're like, come on. Your gas light's been on for a while. Let's just preface it with that. And you're trying to get to the gas station. Light turns green. You're like, go. You're like getting closer, and then your engine goes, the engine died. Does your car immediately stop? Why not? Your inertia is in motion. It wants to continue moving. And the hope is you can drift into the gas station. Okay? It's the same thing here. Here's the rocket. What is it? Firecracker, rocket, whatever. Spaceship. Here's the boosters. After the boosters stop, does the rocket immediately stop moving? Why not? And inertia is motion. The inertia is in motion. And so it's like, I just want to keep on going. So it becomes in free fall at that point in time. Okay? So this is just the first phase. And the position at that point and the velocity at that point become the initial position and the initial velocity for the second point, second phase. Okay, and this becomes free fall. Okay, and you reach your highest point, your velocity is 0. Good with that? Okay, here's one more pitfall that I have seen, for whatever reason, after this worksheet, some of you want to say that acceleration from here on out is always equal to negative 9.8 meters per second squared. It's like, oh, that's great. Like, let's put negative 9.8 for every acceleration. Like, no, that is a special case. That is only when it's in free fall. Okay, only when gravity is the only force acting on it. It's not touching anything. Notice right here, there's some other forces going on besides gravity. Acceleration is not negative 9.8. So do not put acceleration is always equal to negative 9.8 from here on out. Sometimes, if it's in free fall, yes. But if a car is rolling down the road, it is not in free fall. Okay? Good? All right. I'm going to do a quick little experiment. I'm going to take a basketball and I'm going to throw it straight up. Okay? I'm going to do it with a motion detector. I want you to draw the position versus time graph, velocity versus time graph, and acceleration versus time graph of this whole process. So all three graphs, position, velocity, and acceleration as a function of time. Position versus time, velocity versus time, acceleration versus time graphs of me throwing a basketball. Up, straight up, coming back down. That's kind of fun. Okay, everybody got a guess? Here we go. Hopefully one of those got it. Oh yeah, the first one. Man, that's awesome. That usually does not happen. Look at that beautifulness. That is. All right. Goodness. I just assumed I didn't get it. All right. So right here, from there to there, looking pretty good. How'd we do? Okay. Starts fast in the positive direction, steep, shallow in the positive direction, flat or zero slope, shallow negative, steep negative. Fast positive, slow positive, stops, turns around, slow negative, fast negative. What on a velocity versus time graph tells us acceleration? Slope. Check this out, kids. How would you describe that slope? Is it negative or positive? Negative. Is it constant or changing? Constant. Check this out. So negative 8.6, negative 10, negative, oh, nice, negative 9.8. I don't know if you can read those values. Negative 9.5, negative 10.1, negative 9.8, negative 9.4, negative 9.4, negative 9.4, negative 8. So really close to what? Negative 9.8 meters per second squared. Even at the highest point? Yep. Even at the highest point. Give that. Okay. Give this one a shot. Tell your neighbor. Correct answer is C. If you are tempted to say anything else but C, probably B would be the most tempting wrong answer. That is showing you that you still have acceleration and velocity confuzzled. Okay? Those are two different things. Okay? Your velocity can be measured with a speedometer, what your speedometer reads, what it's pointing to. Your acceleration can be observed by what your speedometer is doing. Okay, how it's moving. In this scenario, the ball starts with initial velocity and is slowing down. This is moving at a constant rate, constant acceleration. 9.8 meters per second squared in the negative direction. This is a warm-up question. You didn't need to take physics to know this one. Correct answer is B, the thrown rock. Okay, this is a warm-up question. Same scenario for this question. Talk to your neighbor. Correct answer is okay. Which rock experiences a greater acceleration after it is released from your hand? Which one experiences a greater acceleration after it's released from your hand? Tell your neighbor. Which one experiences a greater acceleration? The thrown, the dropped, or the same? The same. After it's released from your hand, what other force besides gravity is affecting the rock? Nothing. Both are in free fall after it's released from your hand. There's no other force acting on it. You're not Jedi-ing it. Okay? So they're both in free fall. Both are experiencing the same acceleration. Therefore, both experience the same acceleration for the same amount of time. Therefore, this change in velocity has to be the same. Okay? Big picture advice. Make sure you have an equation or something to back up your intuition. Because your intuition oftentimes is wrong. Okay? Does that make sense? So make sure you've got something to back up your case rather than just your, kind of, Okay. So here's what I mean by this. Or conceptually, here's what's going on. The drop rock in that first second goes from 0 meters a second to 10 meters a second in 1 Mississippi. The thrown rock goes from, I'm making this up, 20 meters a second to 30 meters a second in 1 Mississippi. Both experience the same change in velocity. The thrown rock is definitely going faster, but the change, how much it was changed by, is the same as the dropped rock. You see the difference between the final velocity and the change in velocity. That's that's a distinction to be made. Okay. Have a conversation. Okay, what do you say? Heard B and C. Yep. One way would be to do math to verify it. So what you would do is you would say initial velocity is 0. You'd solve for final velocity. You'd do 1.15 seconds. You started from rest, acceleration, okay? And then you would do that. Another way to look at this is graphically. What would a velocity versus time graph look like? Thumbs up if you have a mental image of what the velocity versus time graph should look like. A dropped rock. Hopefully you pictured that. You go in the negative direction, start at rest, and you got faster. Okay. The fact that this is a straight line means that it is has a constant rate of change. So at half of the time, you have half of the speed. Correct answer is A. Okay. If your rate of change is constant, then at half the time, there's half the change. Okay. You okay with, does that make sense? Like, if this is a straight line, that means it's constantly, like it has a constant change. Therefore, at half the time, it's changed half as much. Okay, if that was not a straight line, that wouldn't be the case. Okay. Same scenario, different question. My recommendation would be to sketch out real quick a position versus time graph. Talk to your neighbor. What do you say? Okay. I'm purposely drawing this right above this because their times are shared. You okay with that? Okay. So you're starting high above the ground, you start slow, and then you speed up in the negative direction. Good with that? At 3 seconds, man, I did not draw that very well. Whatever. Okay, at half the time, you've only fallen that much. Everybody see how that, 1.5 seconds here? You've only fallen this much, less than 22.5 meters. C. You could also do the math. You could also solve for delta x of 1.5 seconds and compare that to 22.5. Okay. All right, same scenario, but this time I'm asking for how fast they're going at half the distance. Thumbs up when you have a guess. Talk to your neighbor. Okay, correct answer is got A's and B's. Anybody on that side? Plead the fifth. All right. You could do this two different ways. Number one, you could do it math-wise. Okay. You use displacement of 22.5, starts at rest, acceleration, and you solve for velocity, final velocity. Okay. The other way you can do it is using your graphs. So half the distance is going to be right there. That comes at that late in the ball game. That time, if you transcribe to this graph, you're going faster than half the speed. B, greater than 15 meters a second. Good with that? Okay. Got a review worksheet due on Monday. Also extra credit if you so choose. And Test Tuesday, Ultimate Frisbee after school.